In this video, we are going to be looking at sine graphs. We'll identify them, transform them, and then we'll actually try and graph a transformed sine function. To begin with, just the idea of, we've looked at trig functions before, and you've all seen the sine, cos, and tan, and you know that sine is opposite over hypotenuse and the other ones. When you relate a sine graph or a triangle onto a quadrant, which is sort of an interesting idea, here I've made up a nice right triangle here. So if this is my angle, this side over here would be my opposite side, and this side would be my hypotenuse. I can look at the relationship between the angle here and these two sides. And specifically, we're looking in this module or in this section at the sine ratio. So I can look at those two. And I could take and change this angle to sort of whatever I wanted. And notice that the greater the angle, the longer that opposite side is. And so it'd be nice to sort of look at the relationship that happens. Notice that I can make a triangle, like way up here I could make one. I could actually slip over to this quadrant and I could make another triangle. Let me just do one. Something like this. There'd be a right angle right there. And if I could keep going, I could do one down there and down here. And actually, when you think about the angles, so that might be a 30 degree, 90 degree, 180, 270, 360. But you could keep going. Like this could be 390, 400, etc. You could go around twice. That'd be 720 degrees. And you could keep going. And so what we can do is we can graph those relationships. Let me show you what I mean. So here, in this graph here, in this quadrant here, I've just graphed the relationship between the cos of an angle, and I've made that equal to x, and the sine of an angle, and I've made that equal to y. And so say the angle is 0 degrees, the cos is 0, try it on your calculator, comes out to 1, sine is 0, comes out to 0. So that 0.10 is this point right there. And the cos of this angle, and as you've seen from the previous section about converting radians to degrees, this would actually be 30 degrees. Anyway, the cos of that is 0.87, the sine of pi over 6 is 0.5, and that's that point right there. And so if you plot these relationships, it turns out that what you come up with, and if you did all the ones in between, you'd come up with a perfect circle, which is sort of an interesting kind of graph. But maybe it might be more interesting to relate, rather than just x and y, maybe I can, on a graph, relate the angle measurement to one of these two. And we're specifically going to look at relating or graphing an angle measurement with its sine value. So if I don't worry about the x value, so on this axis here, which is the x-axis, I'm putting in the angle measurement, and then on the y-axis, this one, I'm putting in what the sine of that particular angle is. And notice the kind of shape that you get. You get something called a sine graph or a sine wave. And you've probably seen lots of different examples of those. But this is what we're wanting to explore today, is to take a look at that sine graph and how I can identify it and maybe massage it a bit. Talking about massaging, here's just some examples of sine waves. This one has to do with tidal height, so the tides and how they go up and down. And you can see that that graph there looks sort of like that one. Pressure in the heart or pressure in your veins. The graph of that, mapping the pressure to time, sort of has this kind of shape to it. Here's another, there's a sound wave, and that one, if you zoom in to each one of those, the thing looks more like that than it sort of does here. Anyway, lots of different examples where you might have some kind of a sine graph. The issue we have and that's what the topic of this is how can I get this one, like this is the title one, how can I define that with some kind of a function when the original sine graph looks sort of like that. It's squished a little bit more, but it sort of looks like that. So how can I make the blue one look like the yellow one? And it turns out that that is all about transformations. And we've seen transformations before. This top one here, we've looked at these transformations and seen that A was a vertical stretch, D was a vertical translation, and then C was a movement left or right, and B was something that squished things left to right. And it turns out that in a sine graph, you have the same kind of thing that happens. In looking at transformations of quadratic functions or others, those are okay, but all of these variables look really good and fairly, distinct when you're looking at a sine graph. Okay, so in terms of trig, I want to relate each one of those things, and it turns out that we have different names, similar names, I guess, but some names are different for each one of those. Because you have a sine graph, there's certain characteristics of it that you can define differently than, say, a quadratic graph. Okay, so let's start with each one of those, each one of these letters, and figure out what it does. So let's do the A one. And you probably sort of have an idea of what it's going to do, but let's do it. So, and you can try it on your own device too. So y is equal to, let's just do sine, so functions sine x. So there is the sine graph, and I can stretch that out a little bit. Looks gorgeous. Notice that it doesn't stop, and so it goes both directions. Also notice that I sort of think of it starting right there, and it goes up, down, and then it starts over again. So those are 2 points that you want to think about. But that point right there is 2 pi. So one revolution, like we saw earlier on another slide, all the way around once gives you one thing. And we'll talk about that when we look at letter B. Anyway, that's our sine graph, and what we want to do is transform that. So let's make another one here. Let's go y is equal to, put a 2 in front. So 2, and then sine of x. Okay, take a look. So here you can really tell that the purpose of something out front of a function is a vertical stretch. So all it did is it took the normal red graph and it stretched that out. Now we can do some other things with that too. So if you want to keep looking at that, you can say, well, let's put a 3 in there. So it stretches that out even more. 4, you get the idea. Something else that you might want to do is maybe make a smaller, like squish it. To squish it, you might think, well, let's put a negative in front of it. But notice when you do a negative, and we're following the blue one, what it did is it just inverted it or flipped it over the x-axis or the theta axis. So it just flipped it over. So that's what a negative does. It didn't flatten it. But rather than saying 1, maybe you could say, well, how about 0.5? Sure enough, 0.5 will squish the thing. So A, the purpose of A, is it's a vertical, like I've said in the title there, stretch, or it's a vertical squish. So it can squish too. And also the other thing that A does is it has a vertical flip. So it reflects over the x-axis or the theta axis. And that's if it's negative. Okay, so that's A. Let's stay with the vertical stuff. So this one's just stretching it, not moving it. Let's go to moving it. So let's draw our basic function again. So y is equal to the sine of x. So there's the basic one. So we're playing now with D, the thing on the end. Okay, so let me just put a bracket there. So that's our normal one. Let's make another one. Y is equal to sine of x. And now notice to get a d here, I can't just put a plus right now because that is going to be a c value because it's inside the brackets. So what I have to do instead of that is I have to finish that bracket and then put something on. So let's put, say, a plus 2. There we go. And as we thought, and as we've seen with the quadratics and other functions, d is just the vertical translation. So the purpose of d is to move the whole graph up or down. That's what d does. And it's what you think. So plus 2 means it moves up 2, minus 2, it would go down 2. So that's the d transformation. Okay, now let's get on to c and b. Now notice in my title here, I put C and B because to get the horizontal translation, moving left or right, so that's what this one's going to do. It's going to move it left or it's going to move right. I need a combination of what C and B are. And you'll see that as I graph one. Let's put our base one on again. Y is equal to sine of x. So that's our base one. And now let's put a value in for C. Okay, so y is equal to sine. And I want to put a value in, I'm doing C. So I'll put x and then I'll say minus, why don't I say pi? Pi, there we go. Okay, now when you look at this initially, you think, well, that's just what has happened there is it has just flipped over. But what actually has happened here is the graph has moved. I'll write my graph over here. Y is equal to sine x minus pi. So this thing here has moved the graph right by pi units. By pi units, or by 3.14. So now take a look back at that blue one and notice that the red one starts here, goes up, comes down, and ends there. Okay, but the blue one, rather than starting there, it's moved over to the right. So now it's starting here, it goes up, and it ends there. So this distance that it, instead of starting here, it started over there. That distance there is a horizontal translation. And the distance, if you look at it, is about 3.14. Here's 5, so this would be 3 here, so it's just over 3. So it's been moved over to the right by pi. Now, one of the problems that you run into is if you have a number in front of the x value, so you have sine. So say if I have a 2 here, and then x minus pi. A lot of people say, well, you're just moving right by pi. But if you have a b value other than 1 right there, it doesn't move over by pi. Let me show you. So let's graph another one. Y is equal to sine, function sine. And then I'm going to put a 2 here, and my x minus pi. Bracket. Okay. Oh, gee, it's a mess now. Oh, at least it's a different color. Let me erase my stuff that I put on there. Okay. So now let's make some sense of this. So, the red one is the normal graph. So that's the normal one. The blue one is the one that got moved over to the right by pi. And I guess what I want to do now is just look at how much it moved over. So the red one started here. Red one started there. The blue one starts here. It had got moved over by pi. The green one, rather than moving over to the right by pi, it only moved over half of that. So it would move over by pi over 2. So with horizontal translation, if they want to know how much you have moved over, another name for horizontal translation by the way, is phase shift. So if you want to know what the phase shift is of of any graph, what you do is you take C and you divide it by B. Okay, so that'll be what your phase shift is. And we didn't play a whole lot with that when we looked at quadratic functions. It was harder to see. But here it's easier to see that, yeah, it didn't move over by pi, it moved over half of that. And that's what that b value, the impact of that b value is. And that's why often we draw the graph like this, or the function like that, as opposed to like this, a sine bx minus c plus d. Rather than writing it like this, we sort of factor that b out so that this shows us indeed what the phase shift is, how much it's moved over. Just that name phase shift, if you've done electricity or look up electricity, the phase of a frequency is an important thing. I'm not an electrician, but I've heard the word phase lots with that. All right, let's turn our attention to B. And B, what we've called in the past is a horizontal stretch. With sine graphs, we'll change that name or add another way of describing that, and that's known as the period of a graph. And I'll show you what that means in a second. Let's plug a graph in. Y equals sine x, normal one. Now, one of the features about this graph is that it starts here. That's what, in my mind, that's what I think it starts. But you could have it start anywhere. So it starts there and it ends right there. Okay? So it looks like to do one period or one whole thing, it takes 6 point something or 2 pi. So from here to here, that distance is 2 pi. So it takes one to do one phase, or one period, not phase, one period, it's 2 pi. I can mess with that. And to mess with that, I mess with the b value. So if I say y equals sine of 3x, that 3 does something to the period of that graph. Now, oftentimes you think, well, 3 is going to make it bigger. Let's in fact see what happens. So let's make another graph here. Y is equal to sine, and this time we're putting a 3 in there, 3x. Okay, now take a look at what happens to the graph. Let me erase my chicken scratch here. So the phase shift of the red one, let me make this a little bit bigger. Maybe I'll stretch it this way a little bit. Okay, so take a look at the red graph and how long it takes for it to repeat. I start here, it goes up, down, right there, it starts over again. So that's a period, and the period there is 2 pi. That's how long it takes to repeat. But you take a look at the blue one, and the blue one starts here, same spot, but it goes up, down, and it starts over again. So right there, the period is only from here to there. And it doesn't come bang on an axis, so just from looking at the graph, it's hard to say exactly what the period is. However, you can use a formula to figure that out. And maybe just before I show you this formula, let's take a look at how many times that thing has a period in the time it took the red one to do once. So the red one took from here to there to repeat itself once. The blue one, it repeated itself there, and then to here, and then, it finished at the same spot there. So it actually, 1, 2, 3, it finished 3 periods in that same time. So to determine the period, what you do is you take 2 pi and you divide it by whatever b is. So in our case, the period of our graph here will be 2 pi divided by b. I put a 3 there. so 2 pi over 3. So the period for that graph, the time it takes to repeat itself, is 2 pi over 3. You could figure that out in degrees, but sometimes it's nice to sort of keep things in terms of radians, just a little cleaner. You could figure that out. I think it's 120 degrees in degree measure, but typically we like to keep things in radian measure. Okay, so the period of a graph is, it isn't b, it's 2 pi divided by whatever b is. Okay, so that's our horizontal stretch squish thing. Maybe just one last thing here that I'll do is give you another graph where I make the thing flatter. So y is equal to sine, and this time maybe I'll put a 0.5. You could put a -2, and what that does is it reflects it over the y-axis. I'm just going to put a fraction like 1 divided by 2. Go over and then hit an x. Oops, x there. So that's the green one, and notice that its period is a whole lot longer. Actually, I can't even see a lot of that. Let me squish it. Oh no. Squish it a little bit. Come on, squish. I'm moving it. Doesn't want to let me. Oh, there we go. There. So you look at the green one, and the green one took from here all the way up and over to there in order to repeat itself once. And to figure out that period of that, you do the same as usual, 2 pi divided by b, and b in this case is 1/2. Complex fraction, you could write it as 2 pi divided by 1/2, or 2 pi times 2 over 1, or 4 pi. So the period of the green graph, the 1/2 x graph, would be 4 pi. That's how long it takes to repeat itself. Okay, so we've looked at A, B, C, and D, and I like to look at them sort of separate, or I like to separate the vertical things from the horizontal things. So A and D, they affect the vertical component of the graph. A is the stretchy guy or squishy guy, and D is the move guy. It'll either move up or down. Inside the brackets here, this is all the horizontal stuff that happens to the graph. And we saw that if I take C over B, that is a horizontal translation. We also called it a phase shift. And it's like all the other transformations. If this sign is minus, it moves to the right. If that sign is positive, it moves it to the left. And then we also looked at B, and that is our horizontal stretch or squish. And we also named that, gave it a name in sine graphs anyway, as a period. Okay, so let me just give an example here of what I might be asking. So I might say here is a function, or a sine function, and I want you to tell me what the amplitude, period, phase shift, and vertical translation are. So to get the amplitude, all you do is you look at the number out front there. The minus, this just tells me that it reflects, but it doesn't tell me what the amplitude is. The amplitude is only that number right there. So I'd say the amplitude is 3. Period is 2 pi over b. So 2 pi divided by b in this case is 1/2. There's another one of those things where you have to invert and multiply. So this one will turn out to be 4 pi. That's its period. The phase shift is c over b. And c in this case is pi. And b is 1/2. And so if I do the same thing as I did here, invert and multiply, I'll come up with 2 pi. And when I tell the phase shift which way it's moving, the horizontal translation, I look at this sign, it's minus, so it's 2 pi to the right. That's which way it would go. Or sometimes in my labs they want a positive there. A positive 2 pi means it's moving to the right. Okay, and then the vertical translation is this number at the end there, so you would just say up 2. It would translate the whole graph up 2. Try one. You do that one. Tell me what all of those things are. Press pause and press play. Okay, hopefully you press play. Amplitude for this one is going to be 2. Period is always 2 pi divided by b. 2 pi divided by b in this case is 3. So the period is 2 pi over 3. The phase shift is c over b, and so it's pi divided by 3. So it's going to move things pi over 3. Since this is a minus, it's moving it to the right. Again, put in a positive there indicates it's going to the right. Or you can just say to the right. Vertical translation, that's number there. Things are moving up by a factor of 1. Okay, just one final thing that we can do is, given a function like this, it might be nice not just to identify the features of the graph, but also to actually graph it and see what it looks like. So here it looks like I only have 2 transformations. The b value is 1, so that doesn't affect the period. There's no d value out the end here. You could say 0, but that's not going to move it up or down. So I'm just looking at this, and I'm looking at this. So the 2 there I know is the amplitude. And pi over 2, because this is minus, it's moving to the right by pi over 2. Okay, let's see if we can graph this. So, just for reference, here's pi and here's 2 pi. And let's draw a graph of that. Okay, whoops. So, the normal graph then is going to go up like this, come down through there, and then come up to there. And it would keep going, but let's just look at that one part. And this, it would rise to 1 and it would fall to minus 1. So the amplitude, the distance from the midline here to the top or from the midline to the bottom, that's always a measurement of 1. Okay, so that's the normal graph. Now let's do things to it. So this 2 is the amplitude. So instead of going up to just 1, it should go up to 2. Okay, so I'm not going to change the shape of the graph. Well, the shape, I guess it's getting taller and lower, but sort of the general idea is going up, and it peaks right here, and it peaks right there. That's the same. And it crosses the x-axis or the theta axis at the same spot. That's the same. It's just that it's taller. That's the amplitude. Now this tells me it goes right by pi over 2. Well, pi over 2 would be right there. Since this is pi, this would be pi over 2. So it says it's moved right by a factor of that. So I'm going to have the same tall graph, but I'm starting here instead of starting over there. Okay, so this might be hard. Okay, oh, and I have to end right there. Okay, so I'm going to go, and I probably have to cross right there. So I'm going to go up and down and back up. So that's sort of what it would look like. Let's bring Desmos in and see if that looks anywhere close to what it should be. Okay, I've got to go Y. Oh, I need to bring it up further. Okay. So Y is equal to 2 sine, and then in brackets theta, or x minus pi over 2. Pi divide 2. Okay, and then let's compare that to our normal graph. Y equals sine of x. Okay, So ours was sort of flat, and then the red one's going to be double high, and notice it got moved over just a little bit. Let me sort of identify those. So the normal graph starts there, ends there, and it goes up to 1 and down to a -1. But the red graph, instead of starting here, it starts over there. And that distance will be pi over 2. And then it goes up. Here, the amplitude of the first one is 1, but my red graph, the amplitude comes up to 2, goes down to -2. Okay, so in this video then, we've looked at sine graphs, and we've seen that the effects of A and B, theta, and C, I'm just trying to do this all correctly here, and D have similar effects that they have on transformations of other things. In trig graphs, we've introduced a few new words. A, we've used amplitude for that. For C over B, we've called that a phase shift. And B, from B, going to B, pi divided by B, it's given us something known as the period. And we also saw that D, the vertical translation, is the same as before. Try some questions with that, and as always, if you have any troubles or challenges, give me a call.